Thank you for watching. I'm Sanqun Gu from Andes Technology. We all know that security topics become more and more important in the field of embedded system. Comparing to desktop computers, small IoT device has less computing power, but the responsibility of protecting sensitive data is not less. In this talk, we will demonstrate how to build a security platform with enhanced IOPMP. The fields I have been working in are SOC architect, SOC security, and algorithm analysis. My experiments is related to IC design, EDA tool, and IP development. I am now working in architectural division of Andes Technology. Today's talk will be split into 4 parts. Firstly, I will talk why do we have an IOPMP. Then I will introduce the IOPMP and our enhancement. In the third part, I will show an example by build a root of trust. In the final part, I will give a brief of Andes entry. So, why do we need IOPMP? Platform vulnerability give hackers a chance to access sensitive data or devices. Therefore, people try to define access rule to control every transaction on a platform in a hardware manner. For RISC-V hard, we have PMP to define the rules to check transaction issue from. For the rest of the bus master, such DMA, IOPMP is in charge of checking the transactions issue from. Let's see an example. These slides depict a platform that doesn't have any IOPMP. Here, we have a high-speed bus in blue and MMIO bus are in green. The direction of arrow indicates the command direction of the bus. We can see when a transaction issue from RISC-V hard can be checked by a PMP. By the way, PMP is part of RISC-V hard in reality. The reason to use 2 different blocks is to distinguish the 2 concepts of transaction issuer and a transaction checker. In the same platform, a transaction issued from a DMA can reach any memory or any device without limitation. That is because no one can check or limit this transaction. Therefore, a malicious software may utilize this weakness to compromise the whole system. If we have an IOPMP in each pass before any transaction reaching its destination, we can enforce a permission check. Suspicious transactions then can be detected. By checking back the transaction's information, the malicious behavior and program can be identified and further can be stopped. So what an IOPMP really is? As we saw in the previous slides, we knew we need both PMP and IOPMP to cover all transactions running on a platform. PMP is for RISC-V hard and IOPMP is for the other bus master. They basically do the permission check in a similar way, one rule by one rule, according to the priorities. That is, it is an ordered rule-based checkers. PMP spec has been ratified and IOPMP spec is still ongoing. There have been several IOPMP proposals in the DEE task group. And this technology added and modified some of features to make it more flexible to fit a variety of platforms. Most of features I will go through later. And now, I just want to mention a couple of them. To concern the access latency, we propose to provide an option to allow an IOPMP to send a command to memory before IOPMP checking is complete if certain conditions are satisfied. Generally speaking, when necessary, such outstanding command can be cancelled without any side effect. For example, an outstanding write command can be cancelled by disabling all byte lengths in subsequent data phase. Besides, in some scenarios, we may need different ways to respond an illegal access. In addition to interrupt, one can choose to return a forged data, silently discard over a bus arrow. From now on, in this talk, we will use IOPMP to refer the proposed IOPMP. To check a transaction, a checker PMP or IOPMP should know who issued the transaction, that is, the issuer of the transaction, while PMP use process mode to distinguish who issued a transaction. IOPMP uses master ID or MID to identify the one issuing a transaction. And MID present one or a group of busmaster with the same permission. However, in some cases, one busmaster may have two or more different permissions. A multi-channel DMA is an example that may have different permissions for each channel. Another example is crypto engine. If reading key, reading writing plain text, and reading writing ciphertext can belong to different permissions, each permission should use one MID. MID can be configurable or hardwired. In our proposal, these MIDs should be fixed before entering REE and not changeable until next boot, which should be enforced by hardware. This is because the fixed MID can provide better protection even though the security monitor gets compromised. Besides, we use a zero MID to represent a trusted master. If a RISC-V heart with a well-configured PMP at the right moment, all transactions from it will be checked by its PMP properly, and then we trust it. While a transaction is issued from a master, the transaction carries the MID of its issuer in the beginning. The MID of a transaction could be modified to 0 by an IOPMP or even be removed. A transaction carrying a 0 MID or no MID means checked and legal. IOPMP will skip checking such a transaction without checking again. These slides depict an example of MID and MID assignment policy. In the top half, there are three types of busmaster. We can see that a RISC-V code has a regulated PMP. We will mention it later. Therefore, it uses a zero MID. That is, all transactions from it are trusted and not checked by any IOPMP. In the middle, there is an untrusted busmaster. It should be marked a non-zero MID. The two-channel DMA on the right should be used different MID for the two channel, so the channel number in use should be passed out. In the bottom half, there are two types of slave device, memory-like device and MIO peripherals. We put an IOPMP for each. We have two rules related to MID modification. When a transaction has been checked by a regulated checker, its MID can be changed to 0. That is the rule 1. Furthermore, if all possible transactions on the bus are checked, there is no need an MID on this bus. This describes a recursive form as rule 2. This is an example. According to the previous rule, we can bottom-up deduce this result. Some busmaster use a 0 MID, some bus do not need an MID. In this proposal, an MID uses up to 14 bits. Each IOPMP rule contains two fields, MID.H and MID.L, to store at most 16 MIDs. When IOPMP doing an MID comparison, the 14-bit MID carried by a transaction is split into upper 10 bits and the lower 4 bits. For every rule, the upper 10 bits are compared to MID.H directly, and the lower 4 bits are encoded in a bitmap style in MID.L. This slide shows how the MID comparison works. By this encoding scheme, an IOPMP ruler can store up to 16 continuous MIDs. Secure boot is in charge of initializing security-related components such as MIDs, PMPs, and IOPMPs. In the proposal, we give PMPs and IOPMPs a basic initialization and lock in highest priority during the stage. We should also define the private regions for each process mode and each master if they have. The data in these private regions may include cipher keys, redundancy, device ID, monitor space, anti-rollback counter, IOPMP control register, and other peripherals control registers. We should also prevent security monitor from running an unwanted memory region. If a PMP or IOPMP is considered as a regulated checker, it should be given a basic initialization in secure boot stage. The initialization should prevent UMO from accessing monitor region and other sensitive data, prevent monitor from execution on unwanted codes, prevent DMA from accessing unwanted regions, prevent non-monitor from controlling IOPMPs, and prevent sensitive data even when the security monitor is compromised. These rules should be locked in highest priority. Besides, we should also ensure a PMP or IOPMP is not initialized by a malicious code running in MO. Therefore, for RISC-V hard that may issue a trusted transaction, a security boot should run on it in the beginning and should initial its PMP according to above requirements. And then we trust the transaction issued from the heart, and the PMP is regulated. For more precise, we should ensure RISC-V hard that want to be regulated has been stored up in a trusted code that is a part of security boot. Otherwise, even the programs in M is not considered trusted. For regulated IOPMP, besides the previous requirements, its control register in an MMIO region should be accessed only by specific trusted programs, such as security boot and security monitor. To achieve this, one should use both PMP and IOPMP. If possible, we recommend make every checkers regulated. We suggest that all possible transactions are regulated. Then, where should we put IOPMPs? There are several ways. We may put them close to devices or close to master, as long as every transaction can be checked by at least one regulated checker. Now I'm using an example to demonstrate how to build a root of trust by PMP, IOPMP, and security boot. This is the example platform for our demonstration. I only depict the related component in the slides, which I showed previously. Let's go into more detail. There is an eFuse to store sensitive data, including two parts, keys and AR counter. Keys are used to encrypt and decrypt in the traffic in the network or data in the off-chip storage. AR counter is an anti-rollback counter for updatable firmware. A crypto engine here is used to perform the encryption and decryption. It can directly access memory, include the cipher tags and the plain text. A key buffer inside crypto engine is used to store cipher keys. They can be accessed only via the MMIO bus. Besides, we put two IOPMP in front of memory controller and the entry of MMIO bus respectively. When a system booting, the very first instruction is in the on-chip ROM, which is considered secure. Sometimes we call the ROM code as zero-stage bootloader or ZSBL. So far, PMP and IOPMP are not enabled, so any access is allowed. Then, if MIDs are configurable, ZSBL can set some of them related to booting at this moment. We don't do too much setting initialization in the ROM code because the cost of a modification in ROM is much higher than in other places. So we want to keep it simple. The other MIDs will be programmed later. Subsequently, we copied cipher keys from eFuse to the key buffer inside the crypto engine. If any key update, for example, in the previous run, new keys are stored in off-chip storage by a key wrap, we can unwrap the new keys by the old key and replace keys in eFuse at this moment. After that, asymmetric DSA and AR counter are used to verify if the first stage bootloader or FSBL in the off-chip storage is the original and up-to-date. If we have two or more FSBL, the selection policy is implemented here. If a new version of FSBL is found, AR counter should be updated accordingly. So far, ZSBL has already finished the access to the eFuse. So from now on, the eFuse region should be denied all access until the next boot. In PMP and IOPMP2, the rules to deny should be in the highest priority and with a sticky log. Besides, the MMIO channel to the key buffer should be also blocked as well by using PMP and IOPMP2. And the crypto engine should be only controlled by designated issuer. In our example, we limited it to ML program, which is security boot and security monitor. Then we can jump to FSBL. FSBL firstly does more initialization and set more MIDs of which masters and devices didn't participate in security boot. FSBL can now verify, select, and load the security monitor into on-chip memory. Before entering security monitor, we should do a series of settings to make all checkers regulated. This slide shows some example of these settings. Basically, we do it according to the requirement we mentioned before. We want to give a better protection of security monitor and limited DMA's access in certain permit regions. Some control registers such as MIDs and IOPMPs should be disabled or limited. Finally, we can jump to the security monitor. That is our example. Speaking of here, we are aware that a security platform can be built on a framework that opens to many participants. Therefore, Andes technology provides an open security framework, Andes Sentry, that is brief. Andes Sentry is an open framework, which is a collaboration among Andes technology, our partners, and ecosystem. It mitigates threat from cyber attack to physical attack. It provides flexibility because users can choose different component or policy according to their requirement, which could be robustness-driven, power-driven, cost-driven, and many more. As to the scalability, it can be adapted to single MCU system, multi-core system, or even a platform built from subsystems. Is trustable because our partners have unmatched domain know-how in this field. They have rich experience in many kinds of certification and are willing to help users to pass those certifications. And this technology also has solid experience in process industry and in platform security. By functions, and these entries cover 4 categories: runtime code integrity, crypto acceleration, physical attack mitigation, and TEE. Those are details. They are delivered by us, partners, and ecosystem. This is our modules included in the NDIS entries. It consists of off-chip storage, on-chip hardware IPs, and software state. As to off-chip storage, it supports up to Year 4 plus security storage, which can mitigate various physical attacks. As to on-chip hardware IPs and components, it has PMP, IOPMP, random number generator, crypto engine, security element, root of trust, security debugger, and many more. By taking advantage of these hardware modules, the software stack provides a security foundation to architect your application. So far, it includes security boot, security monitor, TEE, REEOS, and the crypto library. Those are our partner and the ecosystem. Thank you for attending this session. Now we would like to start the Q&A part.